The topic is partial derivative, and we start with the following example. Actually, this will serve us for different examples. Let's define a function I, a function of temperature and humidity, and where I is the heat index. Now, the heat index defined by the National Weather Service is it's a subjective measure. It adjusts the temperature as it affected by humidity. For instance, we know that we feel worse on the whole day if the humidity is high. We feel worse. So the way we feel, I mean, we are different from each other, but we have a certain sort of uniform measure to include the effect of humidity on temperature. We call it the heat index. And so I is the heat index. T, of course, is the temperature measured in either Celsius or Fahrenheit, or Kelvin if you want. And H is humidity, percent of humidity. And here's some data from the National Weather Service. And we have the following. We'll have H and T. And for, I'm going to give you a short version of this table. I'm going to start with, well, actually, I'm going to start with 50 to 55 to 60 to 65, 70, 75, and 80, and I'll stop right there. And this will be percent of humidity. And here I'll have degrees. I'll start with 90, go to 92, 94, 96, 98, and 100. And this will be degrees Fahrenheit. And I have different data, but the one I'll focus on will be the humidity. The heat index correspond to 96 degrees. So when the temperature is 96 degrees, the variation of the heat index, we feel like 109 with the temperature. That looks like high, but I guess that's the data. Let me double check the printout. Yeah, 96 feel like 109. When the humidity is 50%, you feel like 113 when it's 55%. Sorry, 113. 116 when it's 60. 121 when it's 65. 125 when it's 70. 130 when it's 75. And finally 135 when it's 80 degrees. So we have this row. Okay? So what happened here is if T is our variable, then we have a fixed value of T, which is 96, and everything else, the humidity varies. Likewise, we can look at the column where we fix the humidity at 70%, and let's check the variation of the temperature corresponding to this humidity. So I'm not giving you the whole table. I'm just giving you one row and one column. So we feel the temperature feel like 106 degrees when it's 90 degrees outside and 70 degrees with 70% humidity, rises to 112 and then to 118, 125 we already said at 96. At 98 degrees it feels like 133 degrees if the humidity is 70%, and then finally 141 degrees. If the temperature outside is 100 degrees and the humidity is 70%. In Florida, of course, we may have sometimes close to 100% humidity in the summer. So that's why we feel like really, really hot with the heat index. Now, let's look at different scenarios here. Let's first fix the humidity at 70%. So we are looking at what happened along this column. Okay, so if H equal 70% humidity, what happened? Well, then we're going to define a new function for the heat index I. We're going to say now, because we fixed the humidity, we can treat the function I as a single variable function, g of t. Okay, but in reality, we can write it as as a function of f, which is a two-variable function, f of t, comma, and because h is a fixed value at 70, we'll write it t, comma 70. So we have one variable really, but we still write it as a two-variable function. Okay. Now we're interested to know what is the rate of change, or what is the derivative. Well, the rate of change at 96 degrees, what happened is we hold the humidity at 70% and we start varying the temperature. So we're going to say that the rate of change at 96 degrees, or G prime at 96 degrees, is the rate of change of the heat index I with respect to T when T equals 96 degrees Fahrenheit. Okay, again, those are words WRT with respect to and so on. So how we write it using the limit definition, the limit definition of the derivative? Well, the G prime at 96, by the limit definition of the derivative, is the limit when h approaches 0. As a single variable, okay, it will be the limit of g of 96 plus h minus g of 96 divided by h. What we can write here, instead of this one, we can write it as the limit as h approaches 0 of not g but f, because I want to use the two variable notation. Okay, and the moment of hesitation is really, I suppose, to put on the left h of 96 comma 70. Actually, I'm sorry, I'll write it f of 96 comma 70, like so, equals the limit of f of 96 plus h comma 70 minus f of 96 comma 70 divided by h. Okay. Now, if we want to approximate this, we can choose, because we don't have the actual function as a formula, we can use the table, the data, and what we'll do is we assign h values. For instance, we know that the increment in the temperature is every 2 degrees. So, and notice that the variable here is really the temperature, as you can see, 96 plus h. So, in this case, we're going to approximate this derivative. Let's call it back g of 96 as a single variable by assigning the n and g got mixed up here. So by assigning h the values -2 and 2, and therefore we are looking at t going to equals, for -2 we're looking at 94, and for when h is +2, then 96 plus 2 is 98. So like so. So let's evaluate it on the next page. Actually, I need to keep it in front of me. So on the next page, we'll write the following. G prime of 96 will be, now we can drop the limit because we have a specific value of h. So it will be G of 94 minus G of 96 divided by -2. Okay, the specific values for 94 we have 118. Actually, let me write it first in terms of f. F of 94, 70 minus f of 96, 70 divided by -2. Now we'll write the actual value. So, if you look at the little table that I gave you, when temperature is 94, the humidity is 70%, we have 118. And of course at 96, 70 we have 125. And if you look here, we see -7 divided by -2, so it's 3.5. And we'll talk about the interpretation in a minute. Let's look at what happened if we approximate the same thing, but this time, well, let's calculate now for h equals +2. Okay, so G so this was for h equals -2 and t equals 94. Now we'll do the same thing for h equals +2 and t equals 98. So G prime at 96 will be G of 98 minus G of at 96 divided by +2, or f of 98, 70 minus f of 96, 70 divided by +2. And if you apply the values, you look at the temperature at 98 degrees, the heat index is 133. So we are looking at 133 minus 125 divided by 2, or 8/2, so it's 4. Okay, so we have 3.5 and 4, and what we're going to do, we're going to take the average of the two, and we add them up, and it will be 7.5 divided by 2, or 3.75. So what is the interpretation? Anybody venture to phrase the interpretation here? What this number means? No, you explained it very well. Right, and specifically, what it means that there is a rise of 3.75 degrees in heat index for every increase of 1 degree in temperature, while the humidity fixed at 70%. So we're going to write when H, the humidity, equals 70%, and T equals 96 Fahrenheit, like so, then the heat index rises by 3.75 degree Fahrenheit for every degree increase in T, in temperature. Okay. Now we can treat the same thing. So going back to the graph, the table here, what we did, we held the humidity at 70%. So really, this is G of T. If you look at this data, we can treat this data as a single variable function, G, not G prime, but G of T. Of course, the derivative will be G prime. Okay. Likewise, we can do for the horizontal, for the row. If we hold the temperature fixed at 96 degrees, which will be the next treatment. So now we're going to write part 2 here. We're going to say that if T is held steady at 96 degrees Fahrenheit, then we define a new function, uppercase G, of H, of the humidity, and of course this will be F of 96 comma H. So the temperature is fixed at 96, and the only variable is the humidity, the percent of humidity in humidity. Then the derivative of uppercase G at 70% humidity is the rate of change of the heat index I with respect to H. Okay, when T equals 96 degrees Fahrenheit. So we're going to write the following: G prime uppercase at 70 will be the limit as, again, H approaches 0. The definition of a single variable derivative, the limit definition of a single variable derivative, G of 70 plus H minus G at 70 divided by H. And now let's go back and write it as a two-variable function. So we're going to say, all right, in this case, F prime at T and 70. I'm sorry, 96 and 70. We hold the temperature fixed at 96, so we evaluate it at 70, will be the limit as H approaches 0 of F 96, and here we have 70 plus H minus F 96 and 70 divided by H. Okay, so H now is added to the second variable, not to the first variable, as we evaluated at 70. So, again, we approximate this derivative, G prime, at 70 by assigning different H values and in this case the increment of the increment in the percent of humidity is 5%, so we can go one below and one above, so -5 and 5, such that H will be 65 and 75%. So we'll start with H equals -5, therefore uppercase H equals 65%, and we evaluate here, and you'll say, all right, in this case G prime, uppercase G prime at 70 will be approximated by, and I need to go and approximate it here to put the wiggle notation. Okay, so it's approximated by G of 65 minus G of 70 divided by -5. In F notation, it will be f of 9665 minus f of 9670 divided by negative 5. Okay? The actual numbers, if you go back to the table, for 96, for 65% humidity, the heat index is 121. For 70% is 125 divided by negative 5. So we have negative 4 divided by negative 5, positive 0.8. Likewise, we'll let H equals positive 5, and uppercase the humidity will be 75%. And now we have another valuation of the derivative, but this time it will be G at 75 minus G at 70 divided by positive 5. The two variable function notation, f of 9675 minus f of 9670 divided by positive 5. The numbers for 75% humidity, the heat index is 130. So we have 130 minus 125 divided by 5, and of course this is 1. The average, 0.9. Did you say 1.9? 0.9. Thank you. So what is the interpretation here? It's very similar to what we had before. Let's try the interpretation on the next page. Oh, I forgot to spade. Thank you. I think that hat is doing something to my head. Keep it warm and fuzzy. Interpretation. I'm sorry? Only in the winter. I need a winter hat. I don't wear a hat normally. You know, this hat can stay as long as I go home. My wife will give, we'll look at it, and next thing she's going to burn it. So we're going to say that the heat index.
You should tell her you guys are going out.
Yeah, definitely. The heat index rises by 0.9 degree Fahrenheit. Notice that the heat index is still measured by in Fahrenheit for every percent increase in humidity. So in this case, T equals 96 degrees Fahrenheit, held steady, and the H is 70%, evaluated 70%.